Hey everyone, and welcome back to my science studio. In this lesson, we're going to take a deep dive into naming oxyanions and oxyacids, which are a set of rules that seem very daunting to students at first, but not to fret. We're going to tackle them together, and I'll teach you some really cool memory tricks along the way. So without further ado, let's get into it. So what are oxyanions anyway? Well, they're essentially a type of polyatomic ion. And if you remember from one of my previous lessons, I talked about polyatomic ions. And I mentioned how it says what they are in the word. So if we break it up, poly means many, and atomic means, well, atoms. So putting it together, we get many atoms bound together, and they travel as a group. And the word ion is an atom with a charge. That's why polyatomic ions carry an overall charge, whether that's a positive or a negative. And some examples that you've already seen from me in other lessons include NH4+, which is the ammonium ion, OH negative, which is the hydroxide ion, and as a little quick refresh, if you ever see a hydroxide written to the back of a metal, odds are it's a base. But today we'll be focusing on a specific type of polyatomic ion called oxyanions. And you know what? The name actually gives it away. You see, oxy comes from oxygen, and anion means a negatively charged ion. So oxyanions are negatively charged ions that contain oxygen bonded to a nonmetal. And if you look at the table I provided, or the list from your own periodic table, you'll notice something. All the elements listed are nonmetals, and all of them have oxygen atoms attached. The only difference is that the number of oxygens can either be a 3 or a 4. And a really great memory hack, especially for my college kids out there that are stressing trying to memorize these before a test. Everything in the highlighted 4 oxygens group, so phosphate, sulfate, arsenate, selenate, tellurate, these always contain 4 oxygens. And everything else outside of this 4 has 3 oxygens. So that's chlorate, bromate, iodate, nitrate, etc. And a little charge pattern hack that I want to give you guys that could help is that if you notice that everything in group 7A, they're going to have a -1 charge. Everything in group 6A will have a -2 charge. And phosphate and arsenate, which are in group 5A, have a -3 charge. And then the pattern resets starting from nitrate, so it has a -1, carbonate and silicate is a -2, and borate is a -3. So again, this is just a neat little memory trick to help you memorize your oxyanions, especially for my college students that have to memorize these for their exam. For those of you in high school, maybe your teacher gives you a cheat sheet, I don't know, so definitely double check with your teacher on what they actually give you for your exam. But anyways, so all of these that I just mentioned are your original oxyanions. So I like to call them the OGs. They end in 8. So for example, boron becomes borate, right? Because now it's an oxyanion. There's oxygens bound and there's a negative charge, in this case a -3. Then you got carbonate, sulfate, phosphate. Just be careful with the roots. So for example, carbon becomes carbonate, not carbate. And sulfur becomes sulfate, not sulfurate. And for those of you who have to memorize these, flashcards could be really useful here, knowing when to drop the ending and add an 8, or whether to keep the original non-middle name and then plug in the 8. But aside from that, now what happens when the number of oxygens change? Well, now the naming rules really matter. Let's take this example, PO5 3 negative. You'll notice that now you have 5 oxygens Whereas the original, your OG, right, your starting point, phosphate is PO4 3 negative. If you're adding one more oxygen to your original 8, now you add the prefix per to show that. So now we got perphosphate ion. And yes, you have to write the ion because it is charged. But what if now you have one less oxygen than your 8? Now you change your 8 to an ite. And I want you to think of it like you're taking one bite out of the 8, right? You're taking a bite from your burger, right? You only take one bite. Well, you're only going to remove one oxygen. So for example, if you have PO3 3 negative, right? That looks a lot like phosphate, which is PO4. You removed one, so now you have phosphite. What if now you have 2 oxygens less than your 8? Well, now you're going to add the prefix hypo plus the ending ite. And this works for all oxyanions. So an example is hypophosphite, right? PO2 3 negative. If you have 2 oxygens, your original was phosphate and it had 4. So 2 oxygens less than your 8 becomes hypophosphite. And a neat little trick to help you remember hypo is that in science, for the most part, anytime you see the prefix hypo, that means something is very low. So for example, if someone has hypotension, that means they have low blood pressure. If someone's hypoglycemic, that means they have low blood sugar levels or low blood glucose levels. So the same applies here. If you are hypoite of an oxyanion, that means you have even less oxygens than your original, specifically 2 oxygens less. And yes, the charge for all these oxyanions, whether it's per or 8 or ite or hypoite, notice that the charges do not change when oxygens are added or removed. Okay, let's try some practice examples of these oxyanions. Let's take the first one, ClO4 negative. The original is ClO3 negative, which is chlorate. So if they added one more oxygen here, what does that become? Perchlorate ion. We're adding one more to the 8, hence the prefix per. What about the next one? NO2 negative. Well, the original is NO3 negative, which is nitrite. It's your OG. That's your original oxyanion. But if they removed an oxygen, so now we have one less, right? We went from a 3 to a 2. Now you're taking a bite of the 8, right? So now it's nitrite ion. Number 3, SO2 2 negative. Now the original was SO4 2 negative, which is sulfate. If you removed 2 oxygens, now you're hyposulfite ion. Arsenite, so your teacher could give you something like this, where you have the word and you have to go to the formula. So the arsenite ion comes from the arsenate ion. That's the original. It's AsO4 with a 3 negative charge. So we remove one oxygen so that we get AsO3 to the 3 negative charge, or the arsenite ion. Now let's move on to oxyacids. And these guys are acids derived from oxyanions. They start with H because they contain hydrogen ions that will ionize in water. And remember, these are not binary acids. I talked about how to name binary acids in a previous lesson, so definitely check out that video if you haven't done so already. Instead, oxyacids have more than 2 elements because the oxyanion contains multiple atoms. So let's see how this pattern works. Let's say you have H3PO4. Well, you recognize that this 3 next to the H, the subscript, came from the PO4, right? It was a negative 3 charge. And we recognize this oxyanion. It's phosphate. But now there's a hydrogen written to the front of it, right? So we had a hydrogen that has a +1 charge, and phosphate is a negative 3. So when we cross the charges, we end up getting H3PO4. So how do we name this? Take your 8 and drop the ending, so now it becomes ic acid. So in this example, you have phosphoric acid. But now, what if you have one more oxygen than your 8? Well, similar to how we named the oxyanions, where we added a per as a prefix, the only thing we're going to do differently is that we're going to change the ending so that instead of ending in 8, it's going to end in ic acid. So for H3PO5, we end up getting per phosphoric acid instead of per phosphate, right? But now what if you have one less oxygen than your original 8? So for example, H3PO3. It's a hydrogen in the front, so we know it's an acid, and there's an oxyanion attached next to it. And it came from phosphate. Phosphate is PO4, and now we have a PO3, so we have one less. So instead of phosphite, we're going to drop the ending so it ends in us acid. So together we get phosphorus acid. What if you have 2 oxygens less than your 8? So similar to how we did earlier, you add the prefix hypo to mean something even less. But instead of it being hypoite, now it's hypoous acid. So for example, H3PO2, we have 2 oxygens here versus the 4 that we originally had for the ic acid, right? So now we get hypophosphorus acid. Let's try some other examples. Let's say you have HClO4. Well, we recognize that ClO4 negative, right, that's perchlorate because you're adding one more oxygen from your original 8. But because it's the acid form, you're going to drop the ending so it becomes ic acid. So putting it together, we get perchloric acid. What about this next one? HiO2. IO2 negative is iodite because it's one less oxygen from iodate, which is IO3 negative. So the acid form of this is iodous acid, right? So instead of ite, it becomes us acid. One oxygen less than your 8. In this case, one oxygen less than your ic. What about H3ASO4? Well, ASO4 to the negative 3 charge is arsenate. And we have a hydrogen written to the front. So the 8 drops, and now the acid form is arsenic acid. And lastly, what if you have the name hyposulfuric acid and you want to get to the formula? Well, we know that hypo means 2 less oxygens. And sulfuric came from the sulfate oxyanion, which was SO4 2 negative. So dropping 2 oxygens, we end up getting SO2 to the 2 negative charge. And because this is an acid, we have to write the hydrogen ion in front of this oxyanion to get an oxy acid. So crossing the charges, and again, we don't cross the plus or the minus, we just cross the whole number attached to it. We end up getting H2SO2. And again, remember, the +1 drops and becomes a 1, and we don't write 1s as subscripts, so keep that in mind. In my next video, I'm actually going to be doing a lightning round of practice questions, testing you on all the naming of all the compounds, so definitely stay tuned for that. Until then, please feel free to like and subscribe if you found this lesson helpful. I will see you next time in my science studio. Thank you guys for watching and happy studying.